Okay, so welcome to lecture 21, and we are working PG10A. So go ahead and start working on Model 1, and then I will answer some of these questions. So we're talking about the elimination reaction. So the first question it asks, for the reaction shown in Model 1, what is the functional group of the reactant? Did you write alkyl halide? Okay. What is the functional group of the product? Did you write alkene? What two atoms, so 1B, what two atoms in the reactant are eliminated? Did you write H and Br? Provide the IUPAC name for the reactant. So 1, 2, 3. What's 3? So 1 bromo, 2 methyl, propane. Is that what you got? Okay. 2B, look at the atoms that were eliminated on what carbons. Indicate the carbon numbers to those atoms located. So carbon number 1 lost the bromine, and then carbon number 2, so this is carbon number 1, carbon number 2 lost the hydrogen. Greek letters can also be used to locate groups instead of numbers. Carbons 1, 2, and 3 would be alpha, beta, gamma. Okay, so let's go ahead and put that on there. Alpha, beta, gamma. On the reactant in Model 1, label the carbon contained in bromine as alpha. Continue and label beta and gamma. These would also be gamma. For the groups that are eliminated, indicate where they are located using Greek letters. So alpha for the bromine and beta for the hydrogen. Elimination is often called beta elimination. Explain what this means. The hydrogen that becomes eliminated, let's say removed, belongs to the beta carbon. Label the alpha carbon and beta carbons in each of the following compounds. Draw the beta elimination products expected from each compound. Okay, so you can do that as I write these myself. All right, so what are we supposed to do? Label. So this is your alpha. And I like to do, okay, what is this? Let's classify. Is it secondary? Yep. So then we have two alphas. Alpha, alpha. And then I like to put in my, oh, sorry, beta. There you got alpha, right? So then we put beta. And then I like to put in my beta hydrogens. Okay. And then we remove the hydrogen and the bromine. So we're going to lose the HBr. Redraw our product. There you go. and then you have one hydrogen still there. This other one here has hydrogens there. Okay, to the next one. This is your alpha. You get it was secondary. So we have two betas. So if we lose the beta hydrogen and the bromine, and we redraw, we get that alkene. And you can go ahead and draw in your hydrogens. Still have those remaining. Okay, this is your alpha. And how many betas do we have? We just have one, and this is a primary, so you only have one beta. Draw in your hydrogens. You lose the H and the Br, and then you redraw that product. 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. There's your alkene product. In each of the above examples, there is only one beta elimination product expected. Once your group has reached the agreement on the above questions, determine why there were not two products. And that's because the first two are symmetrical. So if you had to choose between the beta hydrogens, it didn't matter because these are symmetrical. So they would give you the same products. This one, we only have one beta hydrogen to choose from. Okay, let's do model 2. So this is going to be elimination with multiple beta carbons. Okay. Question 5. For the alkyl halides shown in model 2, label the alpha carbon and the two beta hydrogens. Okay, so this is the carbon bonded to the bromine, the leaving group. So this is your alpha. It's a secondary, right? Because that carbon's bonded to two carbons. So here's your beta. I'm going to draw in the hydrogens. And then you also have a beta here. And I'll draw in that hydrogen. So label your beta carbons. Put an A to the hydrogen that is eliminated when alkene A is formed. So in order to form this, then this compound had to be, that hydrogen had to be taken away. To form B, the carbon-carbon double bond had to take one of these beta hydrogens. All right, question number 6. Alkenes that are more substituted are more stable. That's important. Alkenes more substituted are more stable. We talked about that in the last lecture. And we also talked about this as Yatsev's rule, that the more stable alkene will be formed, if possible. Draw in two carbons that make up the double bond in compound A. So I just draw in the two carbons. In total, how many R groups? Okay, so what they want you to do in compound A, put your hydrogen there and hydrogen there. 1, 2, that's too many. Okay, 1, 2, 3, 4. I'll draw in the two carbons that make the double bond. Okay, so they're saying draw in this carbon and that carbon to make the double bond. In total, how many R groups, not hydrogen, are attached to these two carbons? So you have 1, 2, 3. So did you come up with 3? 3 carbons? Draw in 2 carbons that make up the double bond in compound B. So there's your carbon and there's your carbon that make up the double bond in compound B. In total, how many R groups are attached to these carbons? So did you get 1 carbon? Which alkene would be more stable? A. A is more stable. That would be a tri-substituted. You see how B is mono-substituted? You can draw in your hydrogens if you want. Once your group has reached agreement on the above questions, determine which compound, A or B, would be your major product. Did you say A would be your major product? Because a tri-substituted alkene is thermodynamically more stable than a mono-substituted. Zatsev's rule states that the more substituted alkene will be the major elimination product. Does your answer 7A agree with Zatsev's rule? Did you circle yes? Because the tri-substituted alkene is A. All right, now number 8, I expect you to draw both compounds. I want you first to label the alpha and beta carbons. And I'm going to tell you on your additional problems, if you don't label your alpha and beta carbons and show me the elimination electron flow arrows, I'm going to take off a half a point per problem. So let's do number 8. How I see you do number 8, how we do it, is how I expect to see your elimination problems when I grade. Okay, so the first thing I want you to do is find your leaving group, and that's your alpha. And then I want you to classify that. That's a secondary. So that means you have 2 betas. You have this beta, and you have this beta. Okay, and then you draw in your beta hydrogens. This has 1. This has 2. And so when a base comes in, let's put base here, it's going to take which one? It's going to take the carbon, the hydrogen that is the least. And then you say, okay, that's tri-substituted. That's going to be your major product. What if you got the other one? So if you took this hydrogen away, what would that product be? That would be the minor. Okay, go to the next one. There's your bromine. That's alpha. Do you see that's the secondary? So we have this beta, we have 2 hydrogens, and this beta would have 1 hydrogen. So your major, your base, is going to take the one with the least, just like that, and that would be 1, 2, 3, 3 carbons. So this is tri-substituted alkene. That's going to be your major. If the base took this hydrogen, you drew that product, you would see that this is 1, 2. That's a di-substituted. And that would be a minor product. And I always ask you for your major product. But if Sapling asks for both, then I want you to do both. Okay, so this is your leaving group. This is your alpha. Do you see that's a tertiary? So we have this beta. You can draw in your hydrogens. This beta. And then this beta. Why did I make that beta a different color? because it obviously has your least number of hydrogens, so that is going to be your major. And then you can see that that is going to be 1, 2, 3. Once again, we have a tri-substituted alkene. If you lose one of these hydrogens, you would get this product, which is the same as the other one, and that is a di-substituted. And you should rewrite these so they look better. So they have like a top and a bottom. You see how that doesn't really have a top and the bottom. So this is a better way. Same thing here. So you see you have sides, you have a top, you have a bottom. All right, so this is di-substituted. This is your major. Now we're going on to Model 3. Model 3 talks about the E2 mechanism. Model 4 is going to talk about the E1 mechanism. So go ahead and try to answer your questions on Model 3. Now I will say that we just did the elimination reaction, so neither one of those were E1 or E2. We didn't focus on that, so now we're going to focus on that. So here we have a base, and we have an alkyl halide. Now you notice how I'm drawing this, a certain rotation conformation, and we have a transition state. Remember? That makes this concerted, like a concert. And that means these bonds are breaking and making at the same time. They're in concert. This is a transition state. There's no intermediate in this reaction, folks. No valley. All right. So we have the base taking this hydrogen, those electrons forming the double bond, and bromine leaving. Now I do want to point out that this line here means they're in the same plane, okay? So it's kind of the same plane. The dashes mean they're going back, the wedges are going at you. So what is 9A? The base removes a hydrogen to form BH. So we will show you over here. There's your base, and it gives the hydrogen. To form BH, what position is the hydrogen relative to the bromine group? So the bromine group is always alpha. That would make this one beta. So you circle beta. What bonds are being formed in the reaction? So when you look at bonds formed, you want to look at the product. So BH is formed, and a carbon-carbon double bond is formed. What bonds are being broken? So we want to look at broken. We look at the starting materials, and we see that a carbon-hydrogen bond is being broken, and a carbon-bromine bond is being broken. How many steps are involved in the E2 reaction mechanism? It's just a single step. 1. So remember your energy diagram? Coordinate. This is basically going to be like, right? So your starting material, and then you have your transition state at the top here, and then you have your alkene product. Focus on the transition state for the reaction in Model 3. How many reactants are involved? Do you see that the base has to take the hydrogen, and in doing so you get a pi bond and the bromine leaves. So we have two things, 1, 2. How many reactants are present in the transition state? Do you see that the base and the leaving group, they're both present? 2. Based on your answer for 10A, explain why the E2 is considered bimolecular. And I think C kind of does the same thing. You see how you have your rate equals, and it should be K times RBr times your base. Okay, so I would write that down. The reaction rate is dependent on both the concentrations of your alkyl halide and your base. And it's concerted. It's a concerted reaction. Is the strength of the base important? Well, obviously it is, because if you have a stronger base, you're going to have a faster reaction. So absolutely important. So you're going to want a strong base for an E2 reaction. The dotted line in the transition state represents a partial bond. This suggests that the bonds are being formed and broken. Hopefully you wrote simultaneously. Concerted. The reaction has no intermediate. It just goes from starting material to product at the same time. So once your group has reached agreement on the questions, compare E2 mechanism to the SN2. Describe the similarities and differences. Well, the similarities are going to be the reaction energy diagram is going to look pretty much the same. You have to have your rate of reaction is going to be both dependent on your alkyl halide and your base. It's both concerted. You're going to find that they're both stereospecific. So where you have backside attack for the leaving group, here you're going to have backside attack for that hydrogen, the beta hydrogen. So that's called stereospecific. So that's the similarities. Now what's the difference? The difference is instead of a nucleophile, you have a strong base. And that means a nucleophile goes after a carbon, the electrophilic carbon. A base is when your nucleophile goes after a hydrogen. Okay, so we're talking acid and base. And so you're going to have a strong base, and that's the difference. So then the products will be different. The only way you can get a carbon-carbon double bond is if you have elimination. Okay, so it says here, stereo effects are minimal in the E2 reaction. A more substituted alkene is more stable than a less substituted. Determine the order of reactivity of alkyl halides in the E2 mechanism. Okay, so this is a little different. Okay, so when we talked about SN2, what did we say? We said allylic and benzylic, and then we said methyl, primary. These are all going to be faster, and then secondary. And we have no tertiary. Okay, tertiary is not going to react in an SN2 reaction. They're too hysterically hindered. Well, in an E2, we get tertiary is faster than secondary, which is faster than primary. So the more substituted alkyl halide will undergo E2 reaction. And you're also going to see that this is also the same pattern of reactivity for E1. Okay, now we're going on to Model 4. Model 4 is our last model before doing the additional problems. So as I write this elimination reaction down, you can go on and answer your questions. Okay, for the E1 mechanism shown in Model 4, how many steps are in the E1 mechanism? So 12A. You see step 1 and step 2? So now we have 2 steps. What bonds are formed or broken in step 1? So in broken, the carbon-bromine bond. What is formed? Nothing's formed in step 1. What bonds are formed or broken in step 2? We have broken is the CH2H bond, and formed is a new carbon-carbon pi bond. Okay, for the E1 mechanism, which step would be the rate determining step? The slow step, right? So step 1. How many reactants are involved in this rate determining step? Just the starting material, right? So rate's going to be equal K times CH3, 3 carbon bromine. And that's what they're saying here. The reaction rate is dependent only on the concentration of the alkyl halide. That is why you have E1 is unimolecular. It's the rate of the leaving group. And so you can talk about that. Is the strength of the base important in the E1? No, it's not important, because the rate of the reaction is not dependent on this base. The base comes in step 2, and this is a fast reaction. In the presence of a strong base, discussing your groups whether an alkyl halide would react by E1 or E2. This is how you determine whether you have an E2 versus an E1. I think about that Meghan Trainor song. What's that Meghan Trainor song? It's all about that base, all about that base, okay? So if you have a strong base, you need to be thinking E2. Strong base have negative charges. E1 is a weak base. So the difference between a strong base is like sodium methoxide and methanol. Okay, so this is weak. This is an E1. This is strong, E2. Usually they involve heat. This alkyl halide, the reactivity is going to be the same. I think that's what they're going to talk about in the next few questions. Okay, so a carbocation intermediate is formed in step 1. So you see the carbocation intermediate? Based on the stability of the intermediate, which class of alkyl halide would be the most reactive in E1? Tertiary. Compare the first step of SN1 mechanism with the first step of E1. What's the similarities and differences? Okay, well in SN1, and an E1, they both rely on the leaving group to leave. And then they have to form the most stable carbocation. That's a similarity. They got to form the stable carbocation. The differences for the first step, there's no differences in the first step. No difference. Indicate whether methanol is a strong or weak base. Okay, we've talked about it being weak because there's no charge. Indicate whether methanol is a strong or weak nucleophile. If it goes after the carbon, it's a nucleophile and it's still a weak nucleophile. Given your answer to 14C, determine whether a reaction of tert butyl bromide and methanol would give SN1, E1, or mixtures of both. Okay, so let's look at that reaction. So you're just talking about tert butyl bromide. And we're putting it in methanol. Okay, so bromine's going to leave. And what's going to happen then is methanol can come in and you can get a substitution. We'll just go ahead and assume deprotonation. Or that's your alpha. This will be your beta. If methanol comes in and acts as a base, then you're going to get elimination. Okay, so E1, this is SN1. You're going to get both. Okay, so that's another problem. With carbocations, you tend to get both, mixtures of both. Recall that an SN1 reaction can proceed through rearrangements to a more stable carbocation intermediate. Since an E1 mechanism has the same step as the SN1 mechanism, would your E1 reaction be likely to undergo rearrangements? Absolutely. You always got to make the most stable carbocation. Okay, so now you need to work 15B, mechanism. When you work through this mechanism, you want to show that the chlorine leaves. Okay, so here's your leaving group. That's step one. There's your carbon. If you want to, it's nice to draw in your hydrogens so you kind of get an idea of what's going on. Okay, so that's step one. You form the carbocation, but you got to make the most stable carbocation. So that carbocation, let's classify it. It's a primary. So we can do a hydride shift. Which means you switch places. So instead of there, now we have this here, and now that's a tertiary. That's pretty stable. And then the methanol will come and take, this is your alpha, it will take a beta hydrogen. So this is tertiary, you have 3 betas, and it will take a hydrogen that has fewer numbers. So you can see that this beta has 3 hydrogens, this beta has 2. If the methanol takes a hydrogen from less to form your alkene, and that's going to give you your more substituted product. Okay. You can also get a carbocation shift, and you might see something like this. And you'll see these for like ring expansion. And so if you see, oh, it shows you this. Okay, so that's a hydride shift. You can also get a methyl shift. So what happens here is this methyl group will actually move here, and then you get a ring expansion of 6. I try not to, you get a positive there. A lot of times you have to number these to see this. 1, 2, 3, 4, 5, 6. So there you have, this would actually be, so when this moves, then this is carbon number 2. 1, 2, 3, 4, 5, 6. And then the beta hydrogen comes from here. And you get something like this. This is rearrangement of a methyl shift. You saw that in SN1, SN2 reactions. Okay, I'm happy if you can do a hydride shift, but sometimes sapling might have those questions. Your additional questions, 16. It looks like you're going to have to label alpha and beta hydrogens and show that mechanism. Draw, it says all elimination products and circle your major one, okay? And then 17, that's DDT, and yeah, the chloride leaves and you do elimination. So that should be good if you get used to doing your alpha beta, and then your major is going to be the Zatsev's product.